We stopped at the previous video at the Schrödinger equation for the harmonic oscillator, which gives us negative h bar squared divided by 2m, the second derivative of psi with respect to position, plus the potential energy term, which is 1/2 mass times angular momentum square times x square times psi equals E times psi. Let's rearrange this equation a little bit. It's going to be a lot of work, so let's number things. So let's call this equation number 1, and let's rearrange it. Let's factor out 1 divided by 2m times h bar over I d dx parentheses square plus mass times angular momentum times position parentheses square times psi equals E times psi. So let's call this equation number 2. And let's remind ourselves, if we have u square plus v square, we can factor this as u minus iv times u plus iv, right? The reason I want to say this, because here in the bracket term we have an item here plus another item, and both of them are squared. So if you think you can do it this way, you're wrong. You can't, because these are operators. See, d dx and the x, these are operators, so usually operators do not commute. So in our case, uv is not equal to vu, because we have a derivative in here. With this being said, we're gonna induce a new expression. We're gonna call this expression a plus or minus. We're gonna define it as 1 divided by 2m, square root of 2m, times h bar divided by I d dx plus plus I m omega x, and let's call this equation number 3. Okay, so now we want to see if we bring a minus and operate a minus on a plus, we want to see what this gives us. In other words, we want to see what we want to see what a minus a plus is equal to. These are operators, and usually operators are very slippery to work with. So I would advise you to induce like a test function and see what these operators do on a test function. So what we're gonna do, we're gonna go a minus operating on a plus operating on some function f of x. In this case we get 1 divided by 2m times the a minus part, which is h bar divided by I minus I, oh no, sorry, times the derivative d dx minus I mass omega times x. Then we have the a plus piece, which is the same, but there's a plus here instead of minus. D dx plus I mass omega x times f of x. So we're gonna take a look at this term by term, okay? First, we're gonna operate this piece on the function, which is gonna give us 1 divided by 2m, everything is the same, dx minus I m omega x. Now we have h bar divided by I df dx plus I m omega x f. Alright, so here we're gonna do it term by term. So we're gonna go this term times this term, same term times the second part, the little zombie thing, remember? This times that. So we're gonna have 4 terms. So let's carry on. 1 divided by 2m, open brackets. The first term, we get h times h square, I times I is negative 1, right? So we have minus h bar square. And then we're doing a derivative on the derivative. So we get the second derivative of f divided by dx square plus, so we're gonna go this term times the second piece, which is gonna give us the I is gonna cancel. We're gonna get h bar mass omega x, and then we're gonna go the derivative times oh, you see, I almost made a mistake. We're gonna take the derivative on xf, so we have the chain rule here. So this x is not there yet. So and we have d dx of xf, and these are 2 functions, the x function and the f function, minus I is gonna cancel. We have h bar m omega x f df dx. df dx. Okay, see here, it's very important the x comes before the derivative because the chain rule doesn't apply. Plus our last piece, which is I times I is I square. So that's give us a negative. This kills this negative, make it a positive. And we have mass times omega times x square times f. Okay, let's clean things up. So now we have equals, remember this is a minus a plus 1 divided by 2m times h bar divided by I d dx square plus m omega x square plus h bar m omega. Okay, so times f of x. Sometimes I'm gonna write f, sometimes I'm gonna write f of x, okay? So it's the same thing. So now we're gonna get rid of this f of x function because it's just a test function. Finally, we have my a minus a plus equal 1 divided by 2m times h bar divided by I d dx parentheses square plus mass times omega times x square yeah, plus 1/2 h bar omega. This is this. Okay, so now here comes the trick. What is this part here? This piece here is the Hamiltonian, right? This is H. This is the Hamiltonian for the harmonic oscillator. So the Hamiltonian can be written as A minus, A plus, take this piece, move it over there, minus 1/2 h bar omega. With this being said, we can rewrite equation number 3, okay? I mean equation number 1 or 2 as in terms of A plus and A minuses. And in this case, we get A plus, A minus, no, A minus, A plus. So we have A minus, A plus, minus 1/2 h bar omega times psi equals E times psi. You can do the same thing. I would recommend you do it with these A minus, A plus flipped. So if you do A plus, A minus here on the side, A plus, A minus, you should be able to use the same steps, induce a test function, and carry on. You're gonna get the same equation. The only difference is A plus, A minus. This is gonna be a plus 1/2 h bar omega times psi. This is the Hamiltonian, equals E times psi. Let's call this equation number, where are we at? 4? Okay, equation number 4. Alright, so now this is the important part. This is what's gonna solve our equation. I claim that if psi satisfies the Schrödinger equation with energy E, that is H psi equals E psi. So if psi satisfies the Schrödinger equation with this energy E, then there must be A plus psi that satisfy the Schrödinger equation with energy E plus h bar omega psi. This is the claim I'm doing, and we're gonna go to the proof. So let's try to prove it. So okay, all right, so if we go okay, so if we have the Hamiltonian A plus psi equals h bar omega A plus A minus plus 1/2. This is Okay, so the proof goes like this. So the Hamiltonian A plus psi is equal, what's the Hamiltonian? The Hamiltonian, we've defined it earlier as A plus A minus plus 1/2 h bar omega. And we're gonna operate on A plus psi, right? So if we do this, we're just gonna distribute these two. We get equals A plus A minus A plus 1/2 h bar omega A plus times psi, right? Okay, so now we're gonna factor out A plus from both sides. So we have A plus, this is gonna give us A minus A plus 1/2 h bar omega times psi. Okay, carry on a little bit further. We have A plus times A minus A plus minus 1/2 h bar omega times psi plus h bar omega times psi. Finally, we have equals A plus, this here is just the Hamiltonian. This is the same as h psi, this piece here, right? It's the same as h psi, but we know what h psi equal to. H psi is equal to E psi. This is just the Schrödinger equation, plus h bar omega psi. So now we're gonna factor out we're gonna factor out psi times psi, give us E plus h bar omega. There you have it. So our claim is valid. So we claim that if psi satisfies the Schrödinger equation with energy E, then A plus psi satisfy the Schrödinger equation with energy E plus h bar omega. Cool, so now same thing goes. We're gonna do the same claim that if psi satisfy the Schrödinger equation with energy E, then A minus now times psi satisfy the Schrödinger equation with energy E minus h bar omega times A minus psi. Cool. So now there must be a limit. Like you see, like here we're decreasing the energy, because if you remember that the Hamiltonian times psi equals E times psi. If we do this, we operating A minus on this guy, we're gonna keep decreasing the energy, right? H bar omega times A minus psi. And we can't go all the way to negative energy. We have no such a thing. So there must be a limit. So there must be A minus times some psi initial that is equal to 0. So this is a very important piece. This is gonna make us solve the equation, okay? So now we have 1 divided by square root of 2m times h bar divided by I d psi naught dx minus I mass times angular momentum times position times the wave function, the initial wave function. This should be equal to 0, right? So now we're gonna move things around, okay, and try to, you know, just move things around. Okay, so we have the first derivative with respect to x is equal to minus mass times omega divided by h bar times x times y, I mean psi naught. This is just first order differential equation. We can solve this guy, right? So before we do this, let's rearrange a little bit further. Let's divide both equation by psi naught and then multiply dx. So we have d psi naught divided by psi naught equals minus m omega divided by h x dx. The reason we did this because we want to integrate. So if we integrate both sides, at the left hand side we just get natural log of psi naught. At the right side we just gonna get minus mass times omega divided by 2h x squared plus some constant c, right? So moving a little bit further, we get psi naught, it's a function of x, equal some constant, normalization constant, a naught times exponential minus m omega divided by 2h times x squared. There you have it. So now this is the solution for the Schrödinger equation with the harmonic oscillator. This is the initial wave function, okay? And from this we can get the initial energy. So just operate h on psi naught, you should get some initial energy times psi naught, right? And what is h? H is a plus a minus plus 1/2 h bar omega times psi naught. This should be equal to E naught times psi. And moving forward we get psi naught, I mean E naught equal 1/2 h bar omega. So this is the initial energy for this initial wave function for the Schrödinger equation for the harmonic oscillator. But that doesn't solve all the wave functions. This is just the initial wave function. However, we do need psi 1, psi 2, psi 3 and so forth, okay? But that's easy because we have these operators, a plus and a minus. From now on we're gonna call them lowering and raising operators. As you can guess, a minus is a lowering operator and a plus is a raising operator. We cannot operate a minus, a lowering operator, on the initial wave function because it's already done. This is the lowest energy point you can get. Okay, so now if you want to find the general solution for the wave function for the harmonic of the Schrödinger equation for the harmonic oscillator, we have the wave function of any order, of the nth order, x is equal to some normalization constants a of n times a plus to the nth order. So if you want to find the second wave function of the wave function of the second quantum state, you just go a plus. To the third, you go a plus. On the same thing, e times minus e to the minus m omega divided by 2 h bar times x squared, with the energy of e sub n of course n plus 1/2 times h bar omega. Let me rewrite the solution again. So the solution is psi of n equal to some normalization constant a sub n, a plus to the nth power times exponential to the minus m omega divided by 2 h bar times x squared. So if you wonder what is this normalization constant, you can work it out. You can integrate over all space from negative infinity to infinity, and you can find this normalization constant. I may do a separate video for this, but if you just want to know the solution for it, it's a sub n equals mass times angular momentum divided by pi h bar to the 1/4 power times minus I to the nth power divided by square root of n factorial times h bar omega to the n power. So this is your normalization constant. If you wanna see it visually, we're gonna make a beautiful drawing here. So imagine a ladder. And this is the ladder of the quantum state we are on, okay? So the first step of the ladder, this is the most one we are familiar with. So this is energy here. This is the wave function. So this is the typical Schrödinger equation, h psi equal E psi. If you operate on this psi with A plus, you're going to increase in energy. So the second step here, this is the step we proved earlier. So if you operate A plus on psi, you should get the same energy plus h bar omega. If you operate again, these are the set of solutions we just got, the psi of sub n. So a plus square psi, you should get two of these h's, so you get e plus 2 h bar omega. You can operate again, psi, a plus to the third times psi, you get e plus 3 h bar omega. You see the idea? And you can operate down. You can lower the energy using the lowering operator, a minus psi. You get the energy of this quantum state minus h bar omega, and you can operate again. I think you see the idea now. A minus squared times psi, you take 2 of these from the energy, 2 h bar omega, and so forth. However, there is a bottom, there is a limit, and the limit is the initial wave function, psi naught. You cannot go lower than that. There is no energy less than the initial quantum state energy. So here you get all the way, you keep operating all the way to psi naught, the initial wave function, you get the initial energy, E naught. And we're gonna draw a cat here going up the ladder. Okay. Here we go. So this is David Griffiths, Professor David Griffiths. He put this in his book. It's a very beautiful drawing. So this cat starts from some quantum state and keep going up, okay, or keep going down, and there's a bottom limit for this. So there is no upper limit, so the sky is the limit here. So you can increase in energy, you can go all the way to whatever you want. Yeah, this is very, very effective because you can actually program this. You can put it inside the computer code and make it do things for you. That's why we do this. That's why we do this stuff. It's a very effective way of solving equations. So there you have it. This is the solution for the Schrödinger equation for the harmonic oscillator.